Dear students, this is the sixth class of differential equations, and in this class we will learn to solve second order differential equations. And you will come to know that there are several kinds of second order differential equations which will be solved in some consecutive classes. And here in this class we will learn or we will learn how to solve differential equations of the type d2y by dx square is equal to fx, and another kind of second order differential equation, that is d2y by dx square, that is equal to fy. This kind of equation will also be solved in this class. So the process or method to solve these two kind of equations will be discussed in this class. So now come to the second order differential of equation, second order differential equation, ordinary differential equation. So you know that in case of first order ordinary differential equation, the derivative of the in a dependent variable with respect to independent variable has the order 1. So in case of second order ordinary differential equation, the differentiation of the dependent variable with respect to the independent variable has the order 2. So in this case, in this type of equation, that is second order differential equation, terms like d2y by dx square, this kind of terms will be found frequently, because in this case the independent variable is x and the dependent variable is y, and the differentiation is of the second order. So in this sense it is a second order differential equation, and there are several kinds of second order differential equations which we have to solve, and of them our standard form is d2y by dx square, that is equal to fx. And we first will learn how to solve this type of equation. So to solve this type of equation, the method is described here or discussed here. So first write this equation as d2y by dx is equal to fx, and now you can write this d2y by dx square as ddx of dy by dx, and that is equal to fx. So ddx of dy by dx, that is equal to fx. You can write this, or now just to integrate this equation, both sides of this equation. So d of, you can write this as d of dy by dx is equal to fx dx, and integrate, then that will give you dy by dx, that is equal to fx dx plus c. Integration fx dx plus c. C1 is a c1 is a constant. Now again integrate this equation, because you have to find out the value of y. So from here you can write dy is equal to integration of fx dx, then dx, plus integration of c1 dx, and c2 another constant. So from here y is equal to integration of fx dx, then plus c1x plus c2, where c1 and c2 are two arbitrary constants whose values can be calculated from the given boundary conditions that will provide you in some problems. So this is the method, this is the process by which you can solve a second order differential equation having the form of d2y by dx square is equal to fx. Now we should go through some examples. Here are first example is here. You have given the differential equation d2y by dx square is equal to e to the power x, and now you know that this equation is rewritten here, and you can write this d2y by dx square as dx of dy by dx, that is here dx of, you can write from here dx of dy by dx, that is equal to the power x, and from there du of dy by dx is equal to the power x dx. Just integrate both sides of this equation. Left side will provide you dy by dx, and the right hand side is equal to e to the power x plus c1. C1 is the integrating constant, and from here to find out the value of, from here you can also write it dy is equal to e to the power x dx plus c1 dx. Now integrate both sides that equation, dy, that will give you dy is equal to e to the power x dx plus c1 integration c1 dx, and from here y is equal to e to the power x plus, from here c1x, and another constant c2 should be there. And since the second order differential equation has the differentiation of the dependent variable with respect to independent variable is order is 2, so in this case two constants will be found. So in the previous, so this C1 is one constant and C2 another constant. So two constants are also found here. If it would be a first order differential equation, then there would be only one constants. So the number of constant is increases. The number of constant increases with the order of the differentiation. If the form of this differentiation would be d3y by dx cube, then the number of constants should be 3 there. So in this case we obtained two constants. So this is the solution. Y is equal to the x plus c1x plus c2. Now solve the differential equation d2y by dx square is equal to sine x. So the given equation is written here, and you can write this left hand side as d of dy by dx, ddx of dy by dx, that is equal to sine x, and from here d of dy by dx is equal to sine x dx, and just integrate both sides of this equation. Left hand side will give you dy by dx and the right side is minus cos x, because integration of sine x is equal to minus cos x. Then plus c1 is the integrating constant, and from here dy is equal to minus cos x dx, and then c1 dx. Now integrate both sides, so that will give you y is equal to, so here is should be integration sign. So from here y is equal to minus, here remember here is there should be a integrating sign. So y is equal to, after integration you will get y is equal to, or you can write omitting, you can omit d here. Directly you can write y is equal to this, or you can write here integration sign. So y is equal to minus sin x, this will give you minus sin x, cos x integration cos x will give you sin x. So that sin x plus c1 x from here and c2. So this is the solution. Number 3 is here, d2y by dx square is log x, and from you can write that this term is d dx of dy by dx, and from there you can also write that integration first d of dy by dx, that is equal to log x dx, integrate both sides. So dy by dx is equal to 1 by, from here 1 by x plus c1, and again you can write from here dy is equal to 1 by x dx plus c1 dx, then integrate both sides. So from here y is equal to, from here log x plus from here c1x plus c2. This is the complete solution. Now we are here to solve second kind of equations, or equation of the type d2y by dx square is equal to f by cr. This is the right hand side is again a function of y. In the first case, what was the form of this kind of equation? The first case it was, see here, first case it was d2y by dx square is equal to fx, the function of x. But in the second kind of equation, d2y by dx is equal to f function of y. See here, this is, be careful, this is another form, this is another form. So how to solve this equation? To solve this equation you have to substitution. The substitution is dy by dx is equal to p. Just substitute dy by dx is equal to p. So from here you can write d2y by dx square, that is equal to dp by dx, and you can write this as dp by dy, then dy by dx. From the knowledge of partial derivative you can write this, and that is equal to, you know that this dy by dx is equal to p, so p dp by dy. And now substitute this value of d2y by dx square in this expression. You will have that is, the left hand side is d2y by dx square, so that will be replaced by dp by dy, that is there, and the right hand side is fy. So from here you can write p dp, okay, this is equal to fy dy. So now integrate both sides. Integration p dp is equal to integration fy dy, and integration of this term will give you half p square, and the right hand side is integration fy dy. Another constant is the integrating constant is c1 prime, and from here p square is equal to fy dy plus 2c prime. Okay, and from here you know that p is equal to what was it taken, dy by dx. So you can write here dy by dx whole square is equal to, since p is equal to dy by dx is equal to 2fy dy, then plus c1, where c1 is another constant, that is equal to 2c1. This 2c1 is equal to c1, c prime is equal to c1, and from here dy by dx is equal to, so just square root of this on the right hand side. So this should be is equal to plus minus 2 fy dy plus c1, or from here dy is equal to plus minus root over 2 integration fy dy c1 then dx. or y is equal to plus minus integration of this term, that is integration root over 2 integration of fy dy plus c1 dx. And from here you can write y by this term. So y by root 2 integration fy dy c1, that is equal to plus minus dx, because you have, and that will give you plus minus x plus c1. Okay, from this. So this is the process by means of which you can solve this kind of equation, that is this kind of equation d2y by dx square is equal to fy. And from there you finally obtain the result as y by root 2 f y integration fy dy plus c1 is equal to plus minus x plus c2 another constant. So two constants are involving in this solution, c1 and c2. Now come to some examples. The first example is d2x by dt square plus omega square x is equal to 0. Just to write this equation, dx by dt square is equal to minus omega square x. This is equation number 1. Now writing dx by dt is equal to p. Finally, you can write d2x by dt square as dp by dt, and that will give you dp by dx, and this can be written in this fashion, dp by dx and then dx by dt. And from there, so finally we get d2x by dt square is equal to p, because dx by dt is equal to p dp by dt. So in this kind of substitution you can since we have already shown in two previous case and in this case also, that d2x by dt square, that means the double derivative of the dependent variable with respect to the independent variable is equal to actually p dp by dx. So in our next problem, so we can directly write this. Okay, so uh, by writing substitution dx by dt is equal to p, then you can write d2x by dt square is equal to p dp by dx. Now substitute this in this equation. So p dp by dx is equal to minus omega square x, or from here p dp is equal to minus omega square x dx. Now integrate this both side. That will result half p square from the first term, and then it is on the right hand side is omega square, then x square by 2 plus c prime. C prime is the integrating constant. So from here p square is equal to minus omega square x square. These two and these two will cancel out, but 2 should be multiplied with c prime, and that is equal to c1. So minus omega square x square plus c1. Now writing here is also, since c1 is a constant, so I am writing it as omega square a square. Both of omega a are constants. So p square from here, omega square a square, omega square x square plus omega square a square, that is equal to omega square a square minus x square. Or from here p is equal to plus minus omega root over a square minus x square. Or you know that p is equal to dx by dt. So dx by dt is equal to plus minus omega root over a square minus x square. Or dx by root over a square minus x square is equal to plus minus omega dt. You can write this in this fashion. So now integrating this term, that will result to first term will give you, just integrate. Now right here online that integrating both sides of this equation, we get what we get. This term will give you cos inverse x by a. You know that dx by root over a square minus x square is equal to cos inverse x by a, and that is equal to plus minus, and this will give you omega t and another constant, that is theta. So from this relation you can write x by a, that is equal to cos plus minus omega t plus theta. That is done here. Or x is equal to a cos plus minus omega t plus theta. Or x is equal to a cos omega t plus theta, because we know that cos minus theta is equal to cos theta. So this is the solution. Another problem is there, that is y d2y by dx square plus dy by dx whole square. This we have to solve this equation. So the given equation is, you can write the equation is written once again, and from here you can rewrite this equation as d2y by dx x square is equal to 1 by y dy by dx whole square. This is equation number 1. Now just write dy by dx is equal to p, and from here you can write d2y by dx square is equal to p dp by dx. So now substitute these values instead of this in this expression. So this will result p dp by dy, that is equal to, in the right hand side 1 by y is there, and this is equal to p square. So this p and one p from here will cancel. So dp by dy is equal to p by y. Or from here dp by p, this p is taken here, that is equal to dy by y. Now integrate both sides of this equation. Log p is equal to log y, and log c is another constant, integrating constant. So log y plus log c. Or from here log p is equal to log cy. You can write this. Or p is equal to cy. This is equation number 2. And you know, now substitute the value of p, that is dy by dx. That is the cy. And from here, just to rewrite this, dy by this y is equal to c into dx. Integrate both sides of this equation. So that will result log y, then cx plus log a. Log a is another constant, integrating constant. So from here log y by a, if you from this term and this term you can write log y by a, that is equal to cx, or y by a equal to c e to the power cx, and y is equal to a e to the power cx. So the solution is y is equal to a e to the power cx. Another example is here, solve the following differential equation. So this equation is given here, d2y by dx square is equal to k y to the power minus 3, where k is a constant. Now we have to solve this equation, and to solve this equation just write or substitute dy by dx is equal to p, and from here you can easily calculate d2y by dx square is equal to p dp by dy. Now write this, just replace d2 dx square, this d2 dx square by this. So right, doing that, p we get p, then dp by dy, that is equal to k y to the power minus 3. And from here p dp is equal to ky to the minus 3 into dy. Integrate this equation, both sides of this equation. So left hand side will provide you p square by 2, and the right hand side is this k is here, and y to the minus 3, integration of y to the minus 3 is minus y to the minus half of y to the minus 2. This is the integration of this, minus of y minus 2 plus c1 prime is constant. So from here p square is equal to this half and this half will cancel, so minus ky square, and then 2c prime. 2c prime is taken as c1. So p square is equal to minus ky square plus c1, or p from here plus minus root over c1. This can be written, this can be organized as c1, this can be arranged as c1 minus ky square. So p is, p is equal to dy by dx, that is equal to plus minus c1 minus ky square. And from here you can write dy by root over c1 minus k by y square is equal to plus minus dx. Now or from here you can just simplify this. So c1 minus y square minus k, and that y square outside this will give you c1 y square minus k by root over within the root over y square, and this y square will go to the numerator. So this is y dy by root over c1 y square minus k, that is equal to plus minus dx. Integrate this equation. So to integrate this equation, write substitute c1 into y square minus k as z square. From here you can find out z is equal to root over c1 y square minus k, and just differentiate both sides of this equation. 2c1 y dy, since k is a constant, so that is equal to 2z dz, and from y dy is equal to 1 by c1 z dz. Now substitute the values of y dy in this equation, y dy and this value in this equation, the left hand side of the equation number 2, that is equal to from here you can write that y dy, this y dy is equal to 1 by c1, so 1 by c1 is there, z dz is there, and this is equal to z. So that is 1 by c1 integration dz, that is equal to z by c1. You will just substitute the value of z, that is c1 y square minus k, and this c1 is here. So from equation number 2 you can write c1 minus y square minus c1 into y square minus k by c1 is equal to plus minus x, and then because this integration of this term will give you plus minus x plus c2, another integrating constant. So from here just just you can write c1 y square minus k is equal to c1 into plus minus x plus c2, and then c1 y square minus k, just squaring both sides, c1 square x plus c2 whole square. So c1 y square from here, c1 y square is equal to c1 into x plus 2 c2 whole square plus k, or from here y square is equal to k by c1 plus 1 c1, this term will give you c1 into x plus c2 whole square. So this is the required solution. And number four, another one is here, another problem is here. This problem, the problem is here, that is d2y by dx square and e to the power x plus 1 plus dy by dx, that is equal to 0. So in this case, see here, on the right hand side is free-form term including the variable y. That is, so in this case, write dy by dx is equal to p also, and then this equation reduces dp by dx. You know, dy by dx is equal to p, so d2y by dx square is equal to dp by dx. You can easily write this. Then e to the power x plus 1 and dy by dx is, since dy by dx is taken as p, so plus p is equal to 0, or dp by dx, then e to the power x plus 1 is equal to minus p, or from here dp by p, this p is taken here, is equal to minus of dx by e to the power x plus 1. Now that can be written as minus, multiply the numerator and denominator by e to the power minus x. So this is it, e to the minus x dx and e to the minus x into e to the x plus 1. So dp by p is equal to e to the minus x dx by, from this, if you multiply this, so first term will give you provide you 1, and the second term e to the power plus, second term is e to the minus x. So that is here e to the power minus x plus 1. Now just find out the value of d of e to the minus x plus 1. So that is that is equal to e minus e to the minus x dx. So this e to the minus x dx can be replaced by, with the minus sign, can be replaced by d of e to the minus x plus 1. So from this equation you can write dp by p, that is equal to d of e to the minus x plus 1 by e to the minus x plus 1. So this will result log of this term. So log p is equal to log e to the minus x plus 1, then plus log c1, say this is a constant. So from here log p is equal to log c e to the minus x plus 1, or from here p is equal to c1 e to the power minus x plus 1. And now substitute the value of p, that is dy by dx. That is equal to c1 e to the minus x plus 1, or from here dy is equal to c1 e to the power minus x plus 1 dx. Just integrate this. This will provide you y, and that is equal to c1. Then the integration of this is equal to minus e to the power minus x, and the right hand side, that is this, will give x, and c2 is another constant. So the solution is y is equal to c1 x e to the power minus x plus c2. This so in this class you learn how to solve a second order differential equation like this d2y by dx square is equal to fx, and this, and also the kind of equations having the form d2y by dx square. So so this is the end of this class, and you need to just practice and everything will be clear to you.